Hi, welcome back. In this video, we are going to talk about the absolute standard entropy. And this is really an extension out of the third law of thermodynamics, in which we defined that at absolute zero, the entropy was zero. Okay, so really, why is the third law important? Many of our calculations, you probably remember these from Gen Chem, they involve looking up standard thermodynamic properties of molecules. Remember those big tables where we said that the delta S was going to be equal to the sum of the delta S of the products minus the sum of the delta S of the reactants, and we looked up these numbers in the tables? Well, the third law is very important because those values in the table come from the third law. The entropies that are in the tables are tabulated as absolute molar entropies. And so this gives us an unambiguous reference point. And so this is the molar entropy at 0 Kelvin. And so we have that reference point for molecular entropy, where an absolute crystal is going to be 0, a perfect crystal. These other molecules having some molar entropy that's not 0 tells us how far away from perfection it is. This symbol, the circle with the line through it, indicates that the value occurs at 1 bar of pressure, but it does not specify a temperature. To account for the temperature, the entropy changes due to heating must be considered. And so that means that these tables that you look at need to tell us what temperature they are tabulated at. So in your book, it gives us some excerpts of some of the molar entropy tables. And so in this table, we are looking at 298 Kelvin and 1 bar. And if we look through a series of diatomic gases, what we can see is that the gases with the highest molar entropy are the ones that are the heaviest. And so if we compare HF to Br2, Br2 is much heavier than HF. And so we can see that the molar entropy increases with increasing mass. This is really due to the spacing between the rotational and vibrational levels decreasing as that mass gets bigger. Now, if we compare small molecules to slightly larger molecules, in physical chemistry, molecules with 4 atoms are really large. We can see that there really isn't a lot of difference in the range of the values that we get. And so this lets us say that molecule size does not contribute significantly to the molar entropy of the compounds. And this is because as the size of the molecule increases, the number of vibrational modes increase. So remember that our number of modes is 3n minus 5 for nonlinear and 3n minus 6 for linear. So as we get more atoms in our molecules, the number of vibrational modes increase. But at normal temperatures, higher than the ground state, vibrational state, are not highly populated. And so that means that these extra vibrational modes really aren't contributing to this overall energy or this overall entropy of the system. And we can see this in our tabulation of our standard molar entropies. Okay, so remember how we said that these molar entropies have to be at a specific temperature. So to account for the effect of temperature, we have to really adjust our molar entropy to whatever temperature we're looking at. And so we can do this by the definition that the molar entropy at with respect to temperature is equal to the integral over ds. And so this means that we can say that delta S is equal to the integral from T1 to T2 of ds, or that delta S is equal to the entropy at T2 minus the entropy at T1. This is key. So if we do some fancy algebra, basically I'm going to multiply things by a funny one, and I'm going to do my dt's. And so since I have dt on the bottom and dt on the top, and I've got t on the bottom and t on the top, that really I'm not doing anything to the inside part of this integral besides multiplying by 1 to make things look right. So I'm going to erase this so that we can see what's going on a little bit better. This TDS dt, this is equal to CPm, the molar heat capacity at constant pressure. And so if we use this and we do the integral, we find that delta S is equal to Cp times the natural log of T2 over T1. Okay, so let's do an example. Calculate the entropy change in joules per Kelvin for heating 1 mole of helium gas from 300 to 400 Kelvin at constant pressure. And it gives us the Cp, the molar heat capacity, of 20.88 joules per Kelvin per mole. And so I'm going to use this equation that we just solved for, and I'm going to plug things in. And so if I do that, I plug in my Cp, I plug in my T2 and my T1, and I do some arithmetic, I get that the entropy is, the delta S is 6.01 joules per Kelvin per mole, and I need to account for the 1 mole of helium, giving me 6.01 joules per Kelvin. Okay, so this pretty much finishes up chapter 9. You should now have the basics that you need to begin working on all of the homework questions. There is going to be a now try this quiz based on this this set of videos, and so keep an eye out for that. And don't forget to schedule your group meeting appointments for the week.